how do you set up this problem, right? So the setup is, if you take the sign of the pure gradients without noise, you should have the regime where it succeeds, right? You actually get to a first order stationary point. But then if you add this noise distribution, you design a noise distribution such that under this noise, it fails, right? It does not converge. So that's what we would like to see. Does that make sense?
So since you add like random noise to the gradient, so what you actually want to prove is that almost shorten the sign so as the gradient descent will go to that.
Right. You can also polish it into probabilistic arguments if you want, right? But I think like what is sufficient for the assignment is kind of providing intuition why this fails and showing it in the notebook. But if you also prove a probabilistic analysis, fine, that's great. And and regarding the Jupyter notebook, I even pointed out in the ICLR paper on sinus GD where there's an example, and there are, I think, already enough pointers there that give you good intuition of what would be the failure mode. So if you go into that, that's a very useful hint. You will, I think, get an idea. And also, how many of you have done Jupyter notebooks before? Okay, so quite a few, but not everybody. And so that was the other reason I asked you to do that, because it's, I think, good practice these days to, provide not only just a package, right? Like not only a very messy package where people have to figure out how to, how the algorithm works, how the code works, but a much more accessible way to understand code, understand algorithms, right? So it's like the hybrid between a paper and just pure code. It's something in between. And I really like that style for providing easy explanations of algorithms, but still having runnable code. Like if you just give the pseudocode in a paper, that's hiding a lot of details. On the other hand, if it's like very messy, non-commented code, it's impossible to read, right? So this will try to make it modular so that you get the ideas, but you can also tweak and change parameters and actually keep running it, right? So you do both. And so that was the motivation to do the Jupyter notebook, right? I mean, you could potentially just write a few sentences and describe the distribution, and the intuition is conveyed, but it's more I want you to go through the exercise because at least I tell my students, interns, preferably to also release a Jupyter notebook along with their code repository, along with the paper. Right, so that's, I think, a good practice for machine learning. So if you haven't done this before, ask, the TAs, ask many of your colleagues who've done Jupyter notebooks. It's, hopefully not that difficult. It may take a little bit of learning curve, but after that, it will be okay. Any questions there? Yeah, so overall, I think the second assignment is very different from the first one. The first one was pure problem solving. There's a linear path. There's one right answer. The second one purposefully wasn't that, right? And future assignments will also be that way because, this is an advanced graduate course. It has a more research emphasis. And so in that, there isn't one right answer, right? It's really, and all the questions you're asking are great. So keep asking them on Piazza, keep asking them in class. We want you to think more about all the aspects of this, right? So it's not a completely specified problem, and that's almost by purpose. So decide, and as you discuss, there are so many ways to interpret, you understand, right? There isn't only one issue we are tackling, but a whole bunch of them. Any other questions, thoughts about assignments? What about the project? I think I, specified the number of sample project ideas, right? And I also said, if you want to have a project of your own, you can put it in that format as the abstract and submit it. When did we say the deadline was? Next Monday. So, and then where is that also on Moodle? I think we should specify that, make that, clarify how they submit that. Yeah. Great. Any questions on this? Any questions from last week? So we concluded most of the optimization, right? So from now on, we'll use many of those results, but for the rest of the course, we will not go into those details of the optimization like we did up till now. And so that's why it's crucial to have those ideas and intuitions of what we currently know in terms of optimization algorithms, what we can say in the non-convex case, and when it comes to the competitive setting, it's even harder, right? So there is very little we can say compared to convex analysis. But on the other hand, we'll see in many machine learning problems, we are forced to deal with non-convex setting, right? Because we want rich enough models, we want, we are dealt with these non-convex problems. And so that was my motivation to start the course with optimization, so we kind of then use those intuitions for specific machine learning problems. So in this class, what we will do is get to spectral methods, which, so what do we mean by spectral methods, first of all? Anybody? What do we mean by spectrum?
Set of eigenvalues for some matrix or tensor, I guess.
Right, so we'll mostly deal with matrices and tensors. I mean, you could also think of spectrum of continuous signals, right? So if you do signal processing, you will see the analogs there, right? I mean, ultimately, it's like Fourier or some basis in which you measure the spectrum. And there is actually a nice interpretation from matrices to continuous functions, but we will not deal much with that in this class. So that's just a pointer for something beyond that. But mostly in this class, I want to think of matrices, right? So we will extend that to tensors towards the end of this class and over the next class. But first, when we think of a matrix, the main question is, how do we express this matrix? Right? So the standard way to express the matrix is what? Just like columns or rows, right? So you have the set of columns, you have the set of rows. So if we express it in terms of rows and columns, what do we call that basis? Standard basis, right? So a standard basis is where, typically it means the way the signal is specified, right? So in this case, I'm specifying the matrix in terms of where it is, right? Where that entry is, which row it is, which column it is, right? So when I'm going to say it's like the ith row and jth column, right? So that's the standard way we specify a matrix. And so I'll also introduce this standard basis vector. So we'll be finding this useful in a number of places. So a standard basis means what? What's a standard basis vector? Yeah.
It's just like 1 in the ith row and 0.
Right. So it's just like kind of you're having 1 here and then 0 everywhere else, right? This is the ith entry. So can I express the idea of extracting the ith row and jth column element through the use of standard basis? Can I specify it through some matrix operations? So I have this matrix M, and I have some operation on this, right? So some operation that will result in ijth entry. What would that operation be?
Just do EI transpose
Right.
times EJ.
So you're taking inner products, right? And it's important to think in this way because there is no reason for you to measure just in the standard basis. Right? So all of the spectral analysis is really transformation of basis. Right? So there could be a better way to measure matrices and more generally signals, and that's kind of the core of spectral analysis. Right? I mean, we are forced to specify the problem through the standard basis, but that may not be the best basis to do our computations, to do our analysis. Right? There could be a transformation that makes the problem much simpler, and that almost underlies all of machine learning. Right? How do I transform the data and my task to make it simpler, to make it more low dimensional? And so that's why it's important to think of inner products as one way to extract information, right? So I'm measuring my matrix in a certain basis, and extraction of information means I take inner products on that basis. Is that clear? Right, so let's first do symmetric matrices. A lot of this will carry over to the asymmetric case, and we will see that. So let's first do the symmetric setting. I guess symmetric is S. So what is the right basis or the efficient basis to measure symmetric matrix? Again, we'll ask what does efficiency mean, right? But so this is where the eigen decomposition comes, right? And I guess I hope you remember what the eigen decomposition is. I'll first just write it, and then I will kind of give intuitions of why. Right, so this is the eigen decomposition. So in contrast, if you had to write your matrix in the standard basis, how would you expand this? You would say M of ij, right? This is the ijth entry, and then this is like ei, ej transpose. Yeah.
It's very hard to see the board. Are there any light boards?
There used to be, let's see, I think, oh, that's switched off.
Sorry.
These are all the lights there are. No, that's switched off, yeah. All the lights are on. It does look darker today for some reason, right? Is there some lights on that side?
That's better.
Can you switch it on?
No.
It's not working.
Well, I think it's something you look like. Okay.
Yeah. Is that better?
A little. I might be the only person having a problem.
Spot up here, by the way, if someone wants to.
Yeah, if you want to come to the front. Oh, it brightened. I don't know what happened. I guess. Great. Oh, it's there. Okay. The brightness is because it was brighter the previous lectures. I don't know what happened. I guess somebody else adjusted there. Yeah, good. Thanks for pointing it out. I appreciate that. Yeah, so I want you to contrast thinking of standard basis compared to the eigenbasis, right? Like, what do you observe here? What's the contrast?
That's like way more terms.
Yeah, this is like n squared terms, right? Whereas this is just n terms. And you could say, oh, this is symmetric. What about asymmetric? We'll see even for asymmetric case, it's only n terms. right? So that's what I mean by efficiency. It's able to express this in a very compact way compared to the standard basis.
But each UI has n elements.
Yes, so that's the transformation, right? So in a way, you're encoding the information in a different way. You're saying first, let me specify what the basis is, and then let me specify what the measurements are in that basis.
So you're simplifying out one order of magnitude.
Right. Because here it's unstructured, right? This information is just spread out over all the entries. Whereas by reformulating it in terms of basis, we are saying, let's look at eigenvalues and eigenvectors, right? And there are n of these numbers, right? Numbers and vectors. And so I'm changing my basis and specifying the problem in a different way, right? I mean, both will have the same amount of information if nothing further is imposed, right? But how you will get efficiency is by hoping that you can impose further assumptions here or make further modifications by thinking of it in the eigenbasis. I mean, that's what we mean by efficiency, right? Like the efficiency will come if you impose more structure and do computations in a more efficient way based on that. And it's hard to specify directly here. I mean, here you could specify in terms of sparsity, right? But here, if you could do sparsity in a different basis. And that's kind of the intuition between sparsity and rank, right? So if you recall what low rank means, low rank is when you don't have like all n of them, you have only some r of them, right? So then we say it's only rank r if you only need r such vectors to specify your matrix. And so low rank is really, it means like some of the eigenvalues are 0, and so it's sparsity in the eigendomain. And low rank structures really underlie almost everything we do, right? So, and that's what we'll see, some machine learning problems, how you can, impose low rank structures and get this dimensionality reduction, this like filtering of noise, many properties we can obtain by imposing the low rank assumption. So one thing I know there was a recitation on matrices that Shaheen did, and I hope you have the background in linear algebra, but I'll provide one interpretation of eigenvectors that I find it very useful. And actually the subsequent lecture on tensors will use the same one and contrast the two. So that is the variational interpretation, right? So on this, since you've done optimization just before this lecture, you can see this, I think, very clearly, why this is useful. So there I just claim that we can write a matrix in terms of eigen decomposition, right? But what is the optimization viewpoint? Like what do eigenvectors and eigenvalues optimize? So let's just take the top eigenvector. Right, so can I write down the top eigenvector as an optimization problem? What is its optimizing?
Maximize U transpose times AU subject to the norm of U is 1.
Right, so you can write, or M, I'm using M, right, so I will use. So if you recall, this was the Frobenius norm, right? So I hope you recall the Frobenius norm. Frobenius norm is sum of the squares of all the entries, right? So think of this as you're minimizing some reconstruction error, right? So you're saying if I want to approximate my matrix with just rank 1, what should that rank 1 be? And typically you want to, you can always scale these in any way, right? Like, so you usually put the scale as a separate one because for the higher rank that will also come up, right? So it's easier to separate the two, although you don't need to, that's more convenient. So that you make U to be on the surface of the sphere, this is L2 norm, and then you have lambda, right, to be some real number. So typically you do it this way, right? And this can be generalized to any rank R matrix as well, because you can just say, find me all the components that fit my matrix M, but there should be only R of them, right? What is the best way to take R directions and fit my matrix? So this is the general formulation, but there is an easier one for rank 1. So I can do something easier than this for rank 1. So what can I do? How can I reformulate the same problem? Yeah, it's just the quadratic form, right? Or rather maximize, right? Because, I mean, and you can see it this way if you like expand this out, right? Like if you expand, will be a term involving only M, involving only U, and then there'll be the cross term, right? Which is the one you want to maximize. And so we'll just rewrite it in this way. And here I can just put the sphere constraints, because actually the value of this objective will be your eigenvalue, right? The top eigenvalue. So is this problem, first of all, is it convex?
Yeah.
Why not? Yeah, the constraint is non-convex, and then you also have like this quadratic form, right? I mean, if this was positive definite, the quadratic form would be convex, but you have the constraint, right? So this is non-convex, but that's okay. We can do non-convex, right? So I can write down the Lagrangian. So I'm gonna like introduce a Lagrange multiplier and put the constraint, right? So this is the equality constraint. So I'll still maximize over U. And if this were convex, I mean, the duality gap would be 0, and under some conditions, and we would be able to solve, right? But we can still write down the stationary points of this. We can still think about local optima, right? So we can do the first order and second order conditions for this Lagrangian. And we did this in the previous classes, right? So what is the first order condition? So for a vector U to be a first order stationary point, what should it be? What is the condition it should satisfy? Yeah.
It needs to satisfy being an eigenvector of n or some eigenvalue.
And how do you see it from this equation?
Taking the Jacobi with respect to u.
You just take the derivative, right? So if you take derivative with respect to U, right? So if you recall your taking derivatives with respect to vectors, if you are not that familiar, it's very useful exercise to go back and do, right? So here you actually get twice mu because you have like both the sides, right? I mean, there's also the transpose side. If you combine both the equations, it'll become like twice, and same here, you would have 2. And so I can remove the 2 on both the sides, so then you have, right? So if you take derivative with respect to U, this will be the stationary point. Do you see this? So what are the set of vectors which are stationary points? What do we call them? Yeah, so these are the set of eigenvectors, right? And more generally eigenspace if there are repeated eigenvalues. So let's do the non-repeated case because it's easier to think. So this is the eigenvectors or eigenspace more generally. So what is it telling us? What can we say about global versus local optimum here? I mean, in this problem, we know what should be the global. So what should be the global optimum for the original problem? Huh?
They are the same, the global and the stationary points.
Are they the same? Are all the stationary points also globally optimal points? Yeah. So what is the difference?
What's the maximum eigenvalue
That-
of the global optimum, and
that-
other, for example, the smallest eigenvalue should be a minimum, right?
Yeah, exactly, right? So here it includes all the eigenvectors as stationary points, but the global one should only be the top, right? Assuming there is a unique top. As I said, let's make the assumption that there is an underlying decomposition where none of the eigenvalues are the same. Just for simplicity, you can easily extend it to the other cases. So if you make this assumption, there is one unique global optimum, whereas if I just looked at first order points, there are multiple of them. So how many stationary points is that maximum? It's n, right? So n stationary points. So it's potentially, I could get some spurious points, right? If I did gradient descent style algorithms, I could get something that's not the global optimum. But we know there are all these standard algorithms for eigenvectors, and we know how to solve that correctly. So something's going on, right? So what's the reason we don't run into other eigenvectors? What should we do for that? What's the next thing we do, right? We did the first order. What's the next analysis we should do? Second order, right? So does anyone recall or have seen what are the conditions for constrained second order local optimum? We didn't do that in class. We kind of ruled out and said even the unconstrained problem is hard enough. But here we have a constraint, so we need that additional one. So what did we say for the unconstrained problem? We said for the unconstrained, right, it was the condition on the Hessian. We'll do the maximization case because here we are doing maximization. So what did we say should be a condition on the unconstrained? Let's say X star is the point I'm interested in.
So I just have a question about the maximization of Lagrangian.
Yeah.
So it seems like the constraint is included in the Lagrangian. So why then that constraint not condition again? So
why is it what? So can you repeat that?
It seems like the constraint you only view equals 1 is included
Yes.
in the Lagrangian
Right.
in the objective.
Right.
And then it's being included again as a constraint.
Oh, sorry. Yes, this goes away.
So that's
Thank you.
unconstrained.
Yeah. Now it's unconstrained, right? And that's for a fixed lambda, right? So you can do this for every lambda. Sorry, that was a typo. Thank you. Yeah. I mean, that was the whole kind of point, right? We'll move the constraint to the objective and express the Lagrangian. And in the convex case, you can, argue in terms of duality here. We can only kind of write down the stationary points as a function of lambda, right? So that's the difference between the two. So now coming to the second order condition, right? We wanted to briefly I'll give you some intuitions on how to think about a second order condition for the constraint case, which we didn't tackle in our optimization lecture. So for the unconstrained problem, if you recall, what we needed was this strict negative definite for an isolated second order maximum point, right? So for maximization. But here for the constraint, what is the intuition? So let's kind of take it's hard to show this in one dimension. You need more dimensions because that's kind of what will, so think of this as more dimensions, and now let's say there is a constraint, right? And for simplicity, it's just a linear constraint. So if it's not linear, you can kind of do the local linearization. And what's kind of the intuition is, right? So you should really be thinking about the tangent space of your constraint, right? So you are not going to move along the constraint directions because that's a constraint. You're going to move in the tangent space of those directions when you're making the local perturbations. Like if you are writing down your Taylor series, you're only allowed to move in the tangent space of your constraints. And so that's the additional change we'll do here, that for constraint, the change will be that we will, let's say V, so we want this quadratic form to be less than 0, but only for those directions that are perpendicular to the constraint, or more generally, they belong to the tangent space of the constraints. So I agree, we didn't go through this in detail in the previous class, but I hope the intuition kind of helps you see, like, we don't need to test for all directions in the Hessian, right? Because you're not allowed to take certain directions. Because of the constraint, you're constraining the space in which you're moving. And that's why it becomes actually an easier test when you have constraint. It only needs to satisfy in the tangent space of the constraints. Yeah.
In this example, how would one specify the tangent space?
Yeah, so in this case, right, so here I have U transpose U equals 1, right? And in this example, the tangent space is what? So if you have like the sphere, right, at any point, if you are saying, so the tangent space, so let's say this is U. So what would be the tangent space here? I think the figure makes it kind of, much clearer, right? The tangent space should be perpendicular to U. Right, so the tangent space of the sphere constraint, all the V that are perpendicular to that U. Right, so now we can think of the second order derivative. Right, so what would the second order be? I mean, if you recall, it was mu minus lambda u. If I took one more derivative, it would be m, right? So I'm taking the derivative here, minus lambda times I. Right, so I just took one more derivative of the Lagrangian. So what should the condition be in terms of this Hessian? So I should require this to be, the quadratic form to be less than 0, but for only V that is perpendicular to that U, right? So here I'm checking for a particular U to be a stationary point, and so I only look for, seeing if all the direction perpendicular to that stationary point, which is all the eigenvectors, if that's less than 0. Is this clear? So we kind of quickly went over the constraint case because, I was arguing in the previous lectures that's usually much harder to do. But at least in this simple case, the tangent space is easy to specify. We can kind of directly see that becomes, just testing for all directions except the direction of the eigenvector, right? In the space orthogonal to the eigenvector. Is this condition clear? So let's say there is let me call this star actually, because there is the variable and then there is. So now I have like the stationary points are, I said u1 star to un star, right? The true eigenvectors are all stationary points. So which of them will satisfy the second order condition? So let's say, I'm ordering this, right? I'm saying this is lambda star 1 is the top eigenvector. So which of them would satisfy this condition? Let's plug them in one by one, right? So if u is equal to u star 1, what happens? U star 1. Does it satisfy or not satisfy? I think it's clear, right? So here lambda you want to choose is also the eigenvalue, right? So that's another detail. The Lagrange multiplier should be your eigenvalue, right? And the Lagrange multiplier lambda should be chosen as one of the eigenvalues corresponding to, because that's how you would satisfy the first order equation. Because the first order conditions is both a condition on lambda and u together, right? They're coupled. Both the Lagrange multiplier and your maximizer are coupled. And this first order condition is saying if the possible set of stationary points are the eigenvectors and the corresponding choice of Lagrange multipliers are the eigenvalues. Right? So now for the second order, I just need to plug in the values and see which ones satisfy. So if I did this for the first one, what happens? What?
Suppose the biggest or the smallest one?
The first is the biggest one. So if I plug in the top component, what am I doing? I'm taking m, I'm subtracting my top eigenvalue, right? And then I'm asking, let me look at all other directions except the top one, right? So I'm looking at space orthogonal to the top direction. This is nothing but if I, so let me, this is obvious, right? Let me not. So you can simplify this, right? This is nothing but V transpose MV, right? The quadratic form on M minus lambda V transpose V. And without loss of generality, I can make V transpose V to be 1, right? Because all I'm checking is the sign. You can just scale both these quantities, that won't change the sign. So I can make this just without loss of generality to be norm 1. So it's just the quadratic form minus lambda, right? Minus the eigenvalue you're choosing. So what happens on the top direction? This satisfies, right? So we are assuming a strict eigengap. That means in every other direction, it's going to be smaller than the top one, right? That's the definition of the top eigenvector. If you look at the inner product, the quadratic form, in every direction orthogonal to the top eigenvector, it's going to be smaller, right? So what happens if you chose instead the second direction? Is that going to be true? Is this condition true for the second one? What do you think? How many think this is true for the second one? If not, why not?
Well, lambda is the second eigenvalue, and V can be anything, so you can set that equal to the first eigenvalue, or eigenvector, right?
Exactly. So this first eigenvector will be in the space orthogonal to the second eigenvector, right? I mean, it is orthogonal, right? So that's why you can set that and that would violate it. So what is the outcome of this analysis? Did you?
I was going to ask, if you assume that M is nice, its eigenvalues are all...
Yes, that's what I kind of mentioned here, right? It's strictly separated.
Working for orthogonalizing eigenbasis and everything.
I mean, the eigenbasis is orthogonalized, right? So we will, I mean, that comes out as a consequence as well. Here, I'm only doing the top eigenvector, right? So the further similar analysis will also show it needs to be orthogonal for it to be like the most optimal basis. But, you know, in this, and that kind of also is a consequence of these kind of conditions, right? Here it's kind of jumping out and saying you should think of space orthogonal to each direction. But yeah, here I assume the eigengap, so that means there's no kind of this, you know, then otherwise it would be a subspace, right? There'll be multiple, like there's a whole space of vectors where it would be optimal, globally optimal. So what's the conclusion of this analysis? What did we conclude here?
That we can check in the first and second order condition, that we can recover the solution to the maximization problem.
Right, so we can actually get the global optimal solution. Does everybody see that? Why is that? Why are we getting the global optimal here? Somebody else. Why are we getting the globally optimal solution here? How many points are satisfying the second order condition? Just one, right? So you have the global optimality condition, right? So the globally optimal is the only one that satisfies second order condition. So what does it mean about the rest of the eigenvectors? If they only satisfy first order but not second order, what do we call such points? We did that in the previous lectures. Saddle points, right? And can we escape saddle points? We know how to escape saddle points, right? That's where, you know, you can add noise, you can look at all these, as long as you don't start near saddle point, you should be mostly okay, right? And in this case, it's very easy not to be near a saddle point. You just randomly choose your initialization, right? That way then there is some correlation with your top direction, right? Only if you initialize in a space orthogonal to the top eigenvector, you're in trouble, right? Because then you're, not gonna, unless you add noise, you're not gonna escape the saddle points. But that's easy to do. And that's why, why I spent so much time on this problem is this is the simplest non-convex problem I can think of where you can solve to global optimality, right? So it's, has this nice property where just the second order condition picks out only one solution, right? Only the global optimum, and everything else is just a saddle point. And so it's almost like it's all the whole linear algebra packages, everything underlie this kind of principle, right? Because we know how to solve to global optimality, we can recover the same solutions again and again, we can design packages, we can give guarantees, we can use them, right? So that's the foundation of, like all of applied math, machine learning, every field, right? So that's kind of the idea. Compared to a general non-convex problem, there is a lot of structure here that you can just do local search algorithms and get to global optimum. And all the more sophisticated computation of eigenvalues and eigenvectors try to accelerate, try to even make that more efficient, right? So if you go into the linear algebra techniques, you can get all those guarantees of how fast you will converge, what's the robustness to noise, all these issues we will deal with as details, right? But this is the main reason we can even do this, even though this is non-convex. Is this clear?
Sorry, can you explain one more time why B needs to be from the space of tangent vectors?
Yeah, so I didn't kind of completely go into it, but the main idea is if you're locally moving, right? So think of like a local Taylor's expansion. You're going to not move along the constraints, you're going to move in the tangent space. That's what a local perturbation looks like, right? Because you're having a constraint. Like if you didn't have the constraint, you would, and it's hard to see in one dimension, it's really in more dimensions, right? You could move in any direction possible because there's no constraint. But the moment you impose a constraint, right, locally you linearize the constraint and you look at only directions orthogonal to it. And so if you think of a half space, that's easier, right? Because then it's just directly everywhere the orthogonal. Otherwise, it's a local linearization, and you're doing like orthogonal to that. Does that make it clear? Yeah. Yeah, and so we use that, and if you didn't use this property, obviously this would like fail, right? So if you didn't say V is orthogonal to U, this would be vacuous, like you wouldn't get any condition, any point to satisfy it. So it's important to have this condition. Without it, you would not get a meaningful result.
When you are saying like this, where we can use some algorithm to get the global optimal solution, are you saying like we only need to update the U, or we still need to update the Lagrangian variable lambda?
Yeah, so that's the detail, right? So in this case, so what you would do in a problem like this is you would typically like set some value of lambda, right? So run the gradient descent and then pick what's the right lambda, right? So that's how we would typically do. But in this problem, it's a lot simpler, right? Because actually you could do projected gradient descent. You can directly just normalize in every iteration or every few iterations. And if you now extend this to higher order subspace, you can do the same. So generally, you could do projected gradient descent where you do gradient descent, you project onto the constraints. In this case, it turns out to be very simple, right? Because all you're doing is just normalizing. And so what does gradient, ascent look like in this case? It's a familiar method for eigencomputation, right? Or rather a special case of the gradient ascent for a specific learning rate. Right, so that's the, I hope you've seen it in the linear algebra class. We'll just briefly recap, right? So the most standard way to compute the eigenvectors, right? So if you're only computing the top one, what do? You take your matrix M, symmetric matrix, right? And then you multiply with U, you just normalize this and keep repeating this again and again. Right, so you're just kind of keep doing this iteration and then you hope it converges, right? And the reason it converges to the top eigenvector is all these analysis. So essentially, if you're replacing this completely, this means an infinite learning rate, right? Because you're completely replacing your the gradient update with your next, or rather the projected gradient to your next step, right? So this is a special case of gradient ascent because you're just replacing it completely and not stabilizing. So if there is noise and if there are more like other guarantees you need, you choose a finite learning rate. Yeah.
Is there any reason why this kind of gradient descent method would be faster? Like I understand that with convergence, so with the power method. But
the power method is a special case, right? This is just infinite learning rate. Because this is projected gradient. So all you're doing is just setting in the learning rate to be infinite, right? You're ignoring the previous update and just using this. And usually if you assume noise and other perturbation guarantees and you want like online PCA, right, people do a finite learning rate instead. So the power method that you're familiar with is nothing but a variant of gradient ascent for this quadratic maximization problem.
Does the use of shifts have a similar sort of parallel in terms of more like generic optimization methods?
So you mean like regularizing by shifting the matrix and getting better properties?
For like power iteration business.
Right, so there, that's kind of, I think of it as some regularization, right? So just as, I mean, if we regularize, we could get better properties, right? So if you recall, I mean, we were regularizing the Hessian in that cubic regularization method. So there's similar interpretations you can think of here, right? You will get better properties to converge. Yeah.
The matrix is not symmetric, then...
Yeah, so then it's singular values, right? So we'll come to that next very briefly, but any questions here? Right, so I spent a lot of time because I think the underlying optimization problem is, quite like it gives you the general form, for the general constrained versus constrained case, it gives you that contrast. But this is simple enough for you to solve this explicitly and see what the optimization landscape is, right? So this is quite unique for non-convex problem that we can characterize every stationary point, right? Exactly what properties it has, and there's only one stable stationary point, and that's the global optimum. Right, so those are the takeaways, I think, from this that's important. Yeah?
So it seems that with the technique of Lagrange multiplier, we're able to turn the constraint problem into an unconstrained problem. But it seems that the second order condition is still constrained.
Yes, the second order condition will still use the constraints to weaken the condition, right? Otherwise, you require this negative definite everywhere, and that may be too strong, and in this case, in fact, that would be vacuous. Right, so because the constraint is saying you don't need to perturb everywhere locally. You are not looking at Taylor's expansion for all possible perturbations, right? There's constraint, you will only move in certain directions. And so we are using that here. And the Lagrange multiplier is also not arbitrary, right? The first order condition is both on the minimizer, right, or the stationary point, or rather maximizer, and the Lagrange multiplier. Both will be taken into account. They're coupled, right? Inevitably, they're coupled. Yeah.
Just for convenience, you'd also have to take, like the first order condition, you can also write the first order condition on lambda.
Yes, so it's on both, right? So on lambda and mu and u, and here actually you put the constraint, right? So you also say you impose the constraint that was there. So you would, and that's what would make it. Otherwise, it's kind of meaningless, right? So here you impose the constraint. You also write down what the first order optimal point is. And you can see like the whole, like the eigenvalue, eigenvector equation is just jumping out directly, right? It's just coming out from this stationary point condition. Does this make sense? And so for higher order, I won't do this. That's kind of more involved. You have to kind of now have multiple, vectors here, but you can still in principle write down the same conditions. Right, so in fact, maybe I'll give a variant of that as an assignment to check like the conditions for the higher order. But a similar kind of argument will go through. Okay, so that's the main result from the optimization perspective, what we think of the eigenvalues and eigenvectors, right? So the singular one, I'll be very quick because it's nothing but, if you recall your singular value decomposition, right? We now, for an asymmetric case, we had both now two different vectors, right? So for the right and the left singular vectors, you had u and v. And the variational interpretation for this is you take the quadratic form. Instead of the quadratic, it's like bilinear, right? So you're now finding two different directions along the right and the left. So you do the same constraint that they're both on the sphere. You now, instead of one vector on both the sides, you just turn them into two different vectors. And and I think there is all these properties. If you recall, if you look at MM transpose and take the eigenvectors of this. Those would be the UIs, right? And if it's M transpose M, it would be the VIs. So that's like all the linear algebra 101. Right, so you can think of all that in terms of this variational characterization as well. So you can write down for this bilinear form also the first order and second order conditions and check that very similar things happen. Okay. So we now set the stage with linear algebra, right? And yeah, we took longer than expected, but hopefully now we can see its applications, I think, all jumping out once we realize how this is easy to optimize, right? And hence we can use this as a dependable primitive in a number of problems. But any questions before we get to applications of using spectral decomposition? Okay, so how many had seen this optimization viewpoint? Okay, quite a few, well, but I hope, but I wanted to recap that because I think this is an interesting application also of non-convex techniques we thought about. Yeah, so this is nothing but just the recap, right? Like, this was the first one, the Rayleigh quotient. I mean, we call this quadratic form actually, maximizing that as the Rayleigh quotient. And the general framework is the rank, in this case I'll use K, rank K case, right? So if you are asking me what is the optimal subspace, right, of dimension K, such that it fits my data well, right? Rather I'm looking at the projection onto that subspace, that's nothing but the top K eigenvectors, right? So this is the projection principle that if you want to look at the maximizing the trace of the projection, right, that is P transpose SP, you will, the result will be P spanning the top K eigenvectors, right? So what we saw was for K equals 1, but you can also extend it for a general K. So this is the projection principle, but how do we use this in machine learning? Right, so what's the short answer? Like, within dimensionality reduction, what's the simplest algorithm we know of? PCA, right? So what PCA is doing really is projecting this to the top directions, but why is that a good idea? So the main intuition is, you have each data point, you want to project them all to a few directions, right? So the idea is, there can be, in high dimensions, a lot of noise, and you want to separate the signal from noise, right? And the simplest thing you can think of doing is, first of all, you center the data. I just look at centered data because it's, you can always just take the mean and subtract it. So you center it, and then after centering it, you want to look at what is the right directions in which I should measure my data, right? What are the principal bases in which I should measure my data, and that's the PCA, right? Sorry. And I think it's like a quick exercise to see why it would be the top eigenvectors of the covariance matrix. Because I've centered the data, the covariance and correlations are the same, but you can also add the centering term and come to the same conclusion. And I think you all remember the Pythagoras theorem, right, for vector norms. Can somebody tell me what's going on in this expression here? Why is this true? So how can I think of measuring the norm of a vector? Is the norm of a vector dependent on a basis on which I'm measuring? No, right? It's basis free or coordinate free, right? So the norm, I can say I will measure it in some subspace P, and then I can measure it in the subspace orthogonal to P, right? So I can look at separating the norm into these two components, and that will satisfy the Pythagoras theorem, right? Because these two subspaces are orthogonal to one another, so you can just apply the Pythagoras theorem. And so this Pythagoras theorem was crucial because, so there I went from that like reconstruction form to the quadratic form, right? So here I've kind of put that explanation why that would be true even for a general P. So once you do that, then it's kind of clear to see, because if I ignore, this is independent of the P I choose, right? This is just the norm of X. And then I'm just maximizing this trace, right? And so it jumps out that you should take the top eigenvectors, right? So I hope everybody is with me here, right? So this is the explanation for PCA, that you center your data, you look at what are the principal directions in your covariance. So you're making a Gaussian assumption implicitly, right? Because you're asking what's the mean, what's my covariance matrix, let me just look at the most important eigendirections, because this is where I hope the signal is, and maybe the rest of it is due to some other noise, right? So that's the basic dimensionality reduction. Any questions here? Right, so this is where it all started, and you could make a probabilistic interpretation, right? So way you can use PCA in a generative setting, meaning you assume there is some underlying model you want to fit, and let's, for the simplest kind of setting, of course there's a Gaussian model, but if you want to go beyond Gaussian, we can think of mixtures of Gaussian, right? So I'm going to assume there is some unknown mean and unknown variance of the Gaussians, but I'll even make it easier for you. I'll say that all the components are just spherical white noise, right? So all of them have the same covariance matrix, and that's just a sphere, right? So I'll make it easier for you that the only unknown are the mean vectors and maybe the variance of the noise, right? So it's a special case, and this is what we call spherical Gaussians, right? Because the variance is just spherical, okay? And I'll use this notation because we'll also use it in the coming classes. It's quite an easy way to think about a linear latent variable model, right? So here H is nothing but a latent variable, right? Because I don't know from which components it's coming. So what's a mixture of Gaussians, right? With a mixture of Gaussian, first I'm going to do a coin flip of which Gaussian I should select from, right? And then I draw a sample from that. And so do you see I can write it in this form? Because this matrix A is nothing but each column is one of the mean vectors. And H is just a basis vector. So that means if I'm selecting it to be E1, that means I'm selecting the first component, and I'm selecting the first column of A, which is the first mean vector. Do you see this notation here? And this notation is very useful because a lot of like discrete random variable models will instead write it in terms of linear models on basis vectors, right? So H could be, it's a categorical random variable, but instead I'm just writing it in terms of basis vectors, right? So it's easier for me to do a lot of interpretations when I turn a categorical variable into a linear framework. Yeah.
Is this all very similar to any Markov model?
Yes, we'll come to that depending on the time today. Yeah, and so everything else, all the other models will be extensions of this, right? And that's why I'm emphasizing on this notation. In many cases, we'll have a mix of categorical and continuous random variables, and we want one common lens to express this. And the way I find this convenient is to express categorical variables in terms of standard basis vectors. So then you can write everything in terms of matrix vector products, right? So because categorical random variables, all they're doing is selecting one of the standard basis vectors. Is that clear? That's why I'm emphasizing a lot more on this notation, right? There are other ways you can write down what's a Gaussian mixture, but this is, I feel, the cleanest way. How many of you have seen Gaussian mixtures or any other latent variable models written this way? Okay, only a few. But is it clear for the others now? I find this very fruitful, because otherwise, especially a mix of discrete and continuous can be a mess. Right, so here you can see the linearity as well quite clearly, right? It's linear in H, linear in Z. So that also will help us in many ways. And that's why this probability of choosing the component, right, you can also write it in terms of this vector W. Because expectation of H is nothing but the probability of choosing different mixture components, right? Because expectation of H is nothing but in every entry, it's just the probability that you will choose that component. Yeah, so once this notation is clear, I think the rest of it is just linear algebra, right? So even though we had this mix of continuous and discrete variables, you can write down the mean, you can write down the variance, you can write down all the moments of your distribution. And so what is the point I wanted to make here, right? I wanted to connect this to PCA, right? So here I'm assuming a specific generative process, and I'm going to see what will PCA do here. Right? And so what did I do here? I'm looking at the covariance matrix of this mixture model. And if you do a bit of algebra, right, so here we know actually Z is uncorrelated with H, right? Because the way I'm choosing is I'm first choosing the component, then I'm drawing independently, conditionally independently from that component, right? So Z is uncorrelated with H, right? So we'll also use that because the terms here, the cross terms will cancel. And so it's clear that there is a spherical part from the variance, and then there is the part from the mean vectors, right? So what will PCA do here? What's your intuition? So I've already given you this equation, right? So PCA works on the covariance matrix. So what will PCA do? What will it capture?
Find the direction of maximal variability.
Yeah. In this case, what does it turn out to be? I'm giving you this equation. Can you interpret what the top directions will be? What do we know here, right? I mean, in every direction there is at least sigma square, right? Eigenvalue. And here this can only be more, right? And so that's the idea. The PCA will actually pick out the subspace spanning the mean vectors. Right? Or another way to see it is, if you ask for the lowest eigenvalue, what would that be? Let's assume K is, by the way, less than D, right? So I'm assuming there are only few components in high dimensions. I think that's important. Sorry if I forgot to mention that. Right, so let's say there are only 3 components in 100 dimensions. So in that case, what would be the lowest eigenvalue of this covariance matrix? Sigma square, right? Because this is only going to span the top components. And so what the PCA is doing is, in this example, picking out the mean vectors which are important, right? I need to pick out what are the mean vectors, and so once I pick out the subspace of the mean vectors, what more can I do? Like, how do we solve a problem where there are these multiple components or clusters? We do clustering, right? So there's k-means, there's all these bag of algorithms. But on the other hand, if this was in high dimensions, let's say it's 100 dimensions and you only have 3 components, you don't want to be doing k-means directly on the ambient space, right? You don't want to be doing k-means in 100 dimensions. Instead, what do? You take the PCA, first you take the subspace, then you cluster only in that subspace. What do we call this method? Spectral clustering, right? So how many of you have seen spectral clustering? Right, so this is, I'm coming at it from a different angle because I'm saying if there is a generative model like Gaussian mixture, spectral clustering makes sense, right? Because it picks out what is the right subspace in which you should cluster. Is that clear? Right, so I mean, there is actually a bit more nuance here. These are actually not rank k, it's k minus 1 because they're actually linearly dependent, so you also have the mean vector. So you want to like kind of take both separately. That's an additional detail. I will leave it to you to look up in the lecture notes. But the main principle is, if you have high dimensional mixtures, you don't want to cluster directly in the ambient space. You don't want to cluster, there could be a lot of noise. You don't want to, you won't have good guarantees if you try to cluster directly, right? And so this is standard practice that people do PCA, then they do clustering. And this is a generative explanation of why that's a good idea. Does that make sense? Okay, and one thing I emphasized a lot was on this expressing both discrete and continuous random variables in terms of vectors, and that'll give us a common lens in which we can interpret the moments, we can expand all that much more easily, right? Because linear algebra will make it a lot easier to interpret them. Yeah? So that was the idea of like PCA being very useful. So another variant of PCA, so this is PCA, right? So what PCA is doing is it's taking your data, it's centering it, and then it's asking what the principal direction is, right? So I'm now treating the principal direction as my first direction, right? So in this case. But you could do something else. You can transform your data to be white, right? By that I mean like you want it to, the covariance to be identity. Right, so you take your covariance and now you say that I want to transformation of the data such that my covariance of the transformed data will be identity. So how would we do something like that?
Compute the square root.
So the square root, right? So does everybody see y? So let's say I have covariance of x, right? So now if I say W transpose W to be identity, right, then that's given by the square root. And this is nothing but if you take your original data point x and instead linearly transform it, right? So now I'll make xi to be zero mean, right? You can always center it, so let's ignore them. So this is the whitening transform where I'll now define new data points which are linear transformation of my original data points. And now if you take the covariance, because this is zero mean, I can directly do the correlation, right? That's nothing but this expression here. And I can turn that to be identity so that I'm taking the square root. So the whitening transform will also be useful in many ways because, there are different directions can be very pointy, right? Like you could have highly skewed direction, one eigendirection to be much bigger than the other. And whereas the downstream methods, like other methods you do after this, may work very poorly if you have such varying eigenvalues. And so this tries to decouple it. It's not clear what the end-to-end performance will be, right? But it's generally a good practice sometimes to do this if your methods expect like whitened data. And so one application of this whitening comes in canonical correlation analysis. Right, so here now it's not just one set of data points, but two sets of data points. Right? Somehow you want to measure the correlation between two data sets rather than look at only one data set. Right? So far we only looked at one collection of data and we were doing all the dimensionality reduction only within this. Now instead, let's say I have like collection of data points xi, collection of data points yi, and I want to think about dependence between the two, right? Like how is x and y dependent on each other? And there are so many ways to define what the dependence is, right? So the simplest thing is just to compute the correlation, right? Let's say these are only vectors, so I'm going to compute this. Sorry, you want the correlation maybe matrix, right? So what's the downside of just looking at plain correlation? I mean, let's say these had values like 10,000 and this had values like roughly like 0.01, right? So these absolute scales will affect what this correlation is, right? So what the canonical correlation tries to do is it whitens both the data and then it's asking for the correlation among the whitened directions. Right, so you can, so what you're doing is whitening each data set and then you're measuring the correlation. And that's called canonical correlation. And the usefulness is, sometimes you want to ignore the impact of the absolute scale of the data points, right? So you really want to measure in the whitened coordinate system, right, what is the dependence between them. And people use that for various other downstream machine learning applications.
Can you explain the situation again? Are U and X, like UI is corresponds to YI, or is it just two sets of data, or just sets the same?
So XI, sorry. X.
Okay, so X and Y. So you said there were two different sources of data, or they're just?
Yeah, let's say two different sources of data that are correlated, right? So, I mean, CCA by itself, right, is not assuming a specific model. It's saying it's generally a good practice not to directly measure this correlation because it's dependent on the actual scale, right? What the directions are, how skewed one direction is with respect to other, even for each data set by itself, and also the cross dependence. So it's trying to make both the data set look the same and then measure the dependence. Right? Because it's whitening them and then saying in the whitened one, what is the correlation between that? And so in some applications this could be good, right? Because if what I'm really interested is not depending on the absolute scale of the data, but there's, in a way, relative dependence, this is, like CCA will be a better one rather than directly looking at correlation. So that's another dimensionality reduction technique, right? Because I'm asking, find me, so in the CCA, what it's saying is, like, find me a direction, right? So I'll whiten my kind of X data, right? And then let's say WX. And then I'll also whiten my Y data points. And then I'm asking for like the principal direction in this whitened data.
Just to clarify, like the set of XIs and the set of Ys, are those of the same cardinality? And you're kind of looking at how XI corresponds to YI?
Right, exactly.
It's not like I've got like 100 data points and then 1,000.
Yeah, no, sorry. In this example, you're assuming they're all the, yes. I mean, think of it as like at the distributional level, right? I'm asking, how do I measure correlation between two random variables or random vectors in this case?
Okay, so it's like scientist A has measured 10 different things, and scientist B has measured like 10 different things.
Yes.
You're comparing those things that are.
Yes.
Okay.
And this is a form of dependence, right? So the correlation is the simplest form of measuring dependence between two random vectors in this case. And CCA argues that if you whiten that and look at the principal directions, that's a better one in many applications. So I'm not going into the details, but just kind of pointing out that's another way to think of spectral analysis, not just on a single data set, but also on multiple data sets and measuring what it means to think of principal directions. Right? So if I have two data sets, what does a principal direction mean? Right? I could have taken principal direction directly on correlation, right? But in many applications, that's not the right measure because it's dependent on the absolute scales, and the canonical correlation analysis tries to overcome that. Okay? That's mostly the intuition I wanted to give for this model. Since I'm out of time, I will cover the hidden Markov model is the next one. I'll cover it in the coming class as an extension where you can also apply spectral methods. But yeah, thank you.